Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello, Lesson 5, three-dimensional space, classwork exercise. Exercise means pause the video, see if you can do this, and we'll take a look at it. It says here, the following three-dimensional right rectangular prism has dimensions of 3 by 4 by 5. So if you look, the base is a rectangle 3 by 4 and it has a height of 5. Determine the length of AC prime, which is this diagonal. Show a full solution. Okay, so picture a box and you have a ruler or a stick or something, and you put it in the bottom left corner, and it is diagonally, it fits to the top right corner. That's the only way you can get it in the box. That's the longest distance opposite corner to corner of a prism or a box. So they want us to find, and let me highlight it. They want us to find AC prime, which is right here. Let me do it with a straight line this time. And thin. So this is where we are looking. Make it a little thicker. There, that's good right there. So we want to find the length of that. Okay, well, it is forming a triangle. So let me now do the other solid sides. So we can make a triangle from this side here is the height, and this here is the base. So it's a two-step process here. I'm trying to get this so it's right perfect. Now, let's try it one more time. Okay, that's good. All right, so then I want to explain that you need to use this side and this side, and then this side I'll overlap with a dash and thin. So the first thing we want to do is look at the triangle on the bottom, on the floor, if you will, on the base of this. And so if I redraw that, let's see. How about here and thin? So this, if we're looking straight down from the box, top into the box, then we know that these sides are, this one is 3, which is right here, and this side is 4, which is here. So we need to find this side. Well, that's a 3, 4, 5 special right triangle. And how did we know this? Well, if we have, let's do it over here. So this is AB. So this side over here is A, opposite A. The side opposite B is the hypotenuse, and the side opposite C is 3. So since B is the hypotenuse, I'd say A squared plus C squared equals B squared in this situation. And then substitute in the givens. A is 4. C is not C anymore. C we know. C is 3 squared equals B squared. Well, 4 squared is 16, and 3 squared is 9 equals B squared. 16 plus 9 is 25. That equals B squared. And then to get B, we take the square root of both sides, and that will leave us with B equal to 5. So that's how we got this. So now I can change B to 5. So let me do that in green. So this is 5. So that was our base triangle. So now if I draw another triangle, I'll do it right below and rotate it or flip it. Like so, then that is this triangle here. So now I'll label the sides, and I didn't label the sides over here. I should. This was C, this was B, and this was A on the floor. Hopefully that helps. And now we're looking at a diagonal rectangle in space. And now we know that this AC, so here is A, here is C, and here is C prime. AC is 5. CC prime is also 5. And it says to find AC prime, which is this side here. So in order to do that, we need to do the Pythagorean theorem again. So let me call this opposite A, little a, opposite C is little c, and opposite C prime is little c prime. So A squared plus B squared equals C squared. In this situation, it will be, I'll do it over here, A squared plus the other leg is C prime squared equals C squared. And A is 5. C prime is also 5. And that equals our C squared, which we're trying to find, which is AC prime. 5 squared is 25 plus 25 equals C squared. So 50 equals C squared. If I take the square root of both sides, I will end up with C equals the square root of 50. Okay, I can simplify that with a factor tree. It'd be 2 times 25 and 5 times 5. There's my pair of 5s. And the leftover stays under the radical. So the answer to my problem is C equals 5 root 2, but it's called AC prime equals 5 square root 2. So this is the answer. Okay, page 2 brings us to an exploratory challenge, and it says table 1, properties of points, lines, and planes in 3-dimensional space. So we're going back a little bit in time here. I think you were introduced to points, lines, and planes in grade 4. So that was like 6 years ago for a lot of you, maybe 5 for others. But it says, number 1, 2 points, P and Q, determine a distance. PQ, a line segment PQ, a ray PQ, a vector PQ, and a line PQ. So basically what they're saying is if I had a point right here, and I call it P, and I put another point over here, and I call it Q, that would represent a distance between 2 points. It would also represent a line segment. Now let's start thick and red. So here is segment PQ. Okay, let me just move this a little bit. Whoops. Okay. Close enough right there. All right. So there's segment PQ. Or I could draw a ray PQ. Let's do that in blue. So you can still see the red segment behind it. There's the ray PQ. That means it goes on forever, indefinitely, one direction from P going through Q. So P is the starting point. And then finally a line PQ. So if I choose a line, and how about green, thin, then this would be line PQ, going forever in both directions. So PQ, there's a distance, PQ is a segment, ray PQ is the blue one, and line PQ is the green one, and it does have arrows on the end. So there is the diagram for point, segment, line, and ray. Number 2, 3 non-collinear points, A, B, and C, non-collinear. So here's A, here's B, here's C. They're not on the same line. A, B are collinear, B, C are collinear, but A, B, and C are not collinear. Actually, that's the name of the, let me get rid of that. That would be the name of our plane. Did they give us a name of a plane? 3 non-collinear points, A, B, and C, determine a plane, A, B, C. And in that plane, determine a triangle, A, B, C. So they want those points to be in the triangle. So here's A, here's B, and how about C over here? So 2 of the 3 are collinear, but all 3 cannot be on the same line. So if I draw a segment from there to there, segment from here to here, and a segment from here to here, then that would be a plane, a triangular plane on this flat surface here. But they are not collinear. In that plane, it will determine a triangle A, B, C. So I'll name that A, B, and that's not very good, B, A, B, and C. Given a picture of the plane below, sketch a triangle in that plane. So there it is. All right, number 3. 2 lines either meet in a single point or they do not meet. Lines that do not meet and lie in a plane are called parallel. Skew lines are lines that do not meet and are not parallel. So A says sketch 2 lines that meet in a single point. So if I choose this line and make it a little thicker and blue, so here is a blue line that goes on forever in both directions, and I'll draw a red one, and they meet at one point right here. Sketch 2 lines that meet in a single point. So the red line and the blue line meet right there. B says sketch lines that do not meet and lie in the same plane, i.e. sketch parallel lines. So if I do that, here's one, put one right next to it. That shows they're parallel. What shows they're parallel? A little arrow thingy like this. So there they are, on the same plane, never intersecting. And then C says to sketch a pair of skew lines. Okay, this one's going to be a little bit tougher. And so what I'm going to do is I'm going to copy my prior shape. So if I put this right here. Okay, so there's that. Now if I draw another line, let's make it a different color like blue, and draw it through this way like that, representing an intersection of one of those lines there, but not intersecting that. That would like rotate it so it's going up through space. The blue line is not on this plane that the 2 green lines are on. So that would represent a skew line. Okay, page 3 brings us to number 4 in our table. It says, given a line L and a point not on L that you can see right here, there is a unique line through the point that is parallel to L. So in other words, there is only one line that can go through this point that is parallel to this existing point. It has to be on the same plane. It has to have the same slope, if you will, and it has to never cross. So if it has the same slope, it would never cross if it's on the same plane as well. If it's not on the same plane, it could be skew, but we don't want a skew line. So we're going to draw a line L like so. And so that's the same line. And then I'm going just to move it over going through that point like so. Okay, so there is a line parallel to L going through this point right here. That's the only line you can draw that is parallel to L going through that point. Number 5, given a line L and a plane P, so this is plane P, so we usually use an italic letter P here. We do that correctly. Okay, so we usually represent a plane with an italic capital letter. So there's capital P. So given a line L and a plane P, so now I need a line L. I'll make it red. There's a line. And then we need to name it L. So there's line L on plane P. Line L meets P in a single point, or line L does not meet P, in which case we say L is parallel to P. So let me read that. Given a line L and a plane P. So there's line L in red, and there's plane P in the corner. This plane right here is a plane P. So L meets P in a single point. So that could be like breaking up through, think of a pencil poking through a piece of paper. Or L does not meet P at all. So it says sketch a line L that lies in plane P. So there's the L that lies in plane P. And then note here it says this implies that if 2 points lie in a plane, then the line determined by the 2 points is also in the plane. A, sketch a line L that lies in plane P. So there it is. B says sketch a line L that meets P in a single point. So in this first drawing, if I put a dot here and a dot here that are both on the plane, then the line goes through them, then the line is also on the plane. But then if I take and I do this, and let me group these first. And I copy them. I grouped the wrong things, but that's okay. All right, so now this is L. This is line L, but if I rotate it, sketch a line L that meets P in a single point. So now let's move this point. Actually, let's delete it. Try that again. Control C, V, there we go. No, I don't want that dot. Okay, it's giving me that same dot that's not on the line. So let me just do it a different way. Let me just draw it. All right, so let's use blue. Let's make it thinner. And this would be that's a ray. This would be the line. And then you put a point on it that appears to be on the plane somewhere. So this dot is on the plane. Picture this blue line poking up through that plane like that. Line L meets P in a single point. There it is. C says sketch a line L that does not meet P, i.e. sketch a line L parallel to P. So if I had this again, I'll put a line on plane P, and then I'll put another line hovering over, if you will, and sketch a line L that does not meet P, sketch a line L parallel to P. So there is a line parallel to P that is not on plane P. So this red line down here is like this one, it's on the plane. So if I put the two dots here, and this is P, that is on the plane. This line is obviously not on the plane, and they are parallel. Number 6, 2 planes either meet in a line or they do not meet, in which case we say the planes are parallel. A, sketch 2 planes that meet in a line. Okay. Okay, so if I draw a 4-sided figure, let me see, let's just do it with line segments, and I'll do it in black. So if I have a plane like this, so I'm going to make it a little larger though. Okay, so there's my plane. And then I'm going to sketch another plane. Like so. And then where they meet, think of 2 pieces of paper cutting through each other. like so. Okay, so this green one is a vertical plane. The black one is a horizontal plane. They intersect at this dash line. So that would be an example of two planes that meet. One's cutting through the other, and it forms a line. And then it says sketch two planes that are parallel. So that's easy. All I need to do is take this, copy it, put it here, and then do another one. Change its color to, say, red, and move it to, say, here. So that is a distance off, and then I would want to, actually, let's explode that. I want to do something here. Ungroup. All right, so I want to take this segment and drag it back to here. Take this one, drag it back to here, and then use a dash line to show that it's behind. Okay. Like so. That would be two planes that are parallel. Okay, page 4, we're continuing. So number 7 says two rays with the same vertex form an angle. The angle lies in a plane and can be measured by degrees. Sketch the example of the following plane. So I'm going to start by putting a dot right here. So two rays with the same vertex. So that's my starting point of my ray. I will choose one ray to be, well, let's first start by making it a ray and not a line. So there's a ray. Let's make it blue's fine. And I start at the point and go like that. Let me just move that a little. So there's my ray starting at that point. Let's make the point more vivid. That point right there. And then I'm going to do it again with red. So if I make another ray red from the same starting point, like so, then I can say that this is an angle of theta degrees. So there is an angle in a plane from the same vertex, two rays going in a different direction, with a measurable angle in between. Okay, number 8. Two lines are perpendicular if they meet and any of the angles formed between the lines is a right angle. Two segments or rays are perpendicular if the lines containing them are perpendicular lines. So all I need to do is draw a line. Red is fine. And let's just go this way. And then if I draw another line, and let's make it blue, and this way, so long as if only one of these is 90 degrees. Why only one? Because if one is, they all are. Vertical angles are congruent, so those both will be 90. These are linear pair on the blue ray or blue line, so those are 90. If that's 90, this has to be 90 to total 180. A line is 180 degrees. So two lines are perpendicular if they meet and any of the angles formed between the lines is a right angle. So I could have labeled that a right angle, this one, or this one. So long as one is 90, they all have to be. Otherwise, the two lines aren't straight. Then it says two segments or rays are perpendicular if the lines containing them are perpendicular lines. Okay, I guess that's good enough for now. Number 9. A line L is perpendicular to a plane P if they meet in a single point. Okay, so we're going to draw a line perpendicular to a plane P. So here's plane P. Here's a point. I'm going to draw a line through it that's perpendicular, straight up and down like so. And we have to show that it is 90 degrees to the surface like so. All right, so a line L is perpendicular to plane P. So this is line L. If they meet in a single point and the plane contains two lines that are perpendicular to L. So I need two more lines. So that would be perpendicular to L. And that's also perpendicular to L. So there's a 90-degree angle with this green line, a 90-degree angle with this green one. Actually, let's change the color. So let's make one of these green ones, I don't know, blue. Okay, so the red line is parallel to the blue one, or perpendicular to the blue line, and the red line is perpendicular to the green one. Then the blue and green lines are on plane P, then line L has to be perpendicular to the plane, is what this is saying. In which case, every line in P that meets L is perpendicular to L. A segment or ray is perpendicular to a plane if the line determined by the ray or segment is perpendicular to the plane. Draw an example of a line that is perpendicular to a plane. So there it is. Draw several lines that lie in the plane that can pass through the point where the perpendicular line intersects the plane. So I can do this again, choosing a different color, and draw another line like so. Intersecting and perpendicular to the purple one as well. So there's infinitely many, okay? So if the red line does not move and it's perpendicular to the plane P, every line we draw on plane P going through this point would be perpendicular to the red line L. All right, number 10. Two planes perpendicular to the same line are parallel. So if I drew a line perpendicular to both, is what they're asking us to do, that would be a line going through like this, intersecting the top plane at a point, say here, and intersecting the bottom plane at a point, let's say there, and they are perpendicular to the plane, then the planes must be parallel. And while we're at it, let's name these. Let's call that P and that Q. So one line and perpendicular to both planes, the planes must be parallel. Okay, page 5 brings us to number 11. Two lines perpendicular to the same plane are parallel. Two lines perpendicular. So now all we have to do is draw two lines perpendicular to the plane. So I'll choose this, I'll choose, okay, lines, I'll choose red for one. So there's a line perpendicular, and then I'll choose another one, make it blue, and whoops, that one's definitely not perpendicular. Whoop. Okay, there we go. Two lines perpendicular. So I want to show that they're perpendicular by drawing right angles to the plane like so. So the two lines perpendicular to the same plane are parallel. Sketch an example that illustrates the statement using the following plane. So there it is. So they actually would intersect at, say, this point right here. Think of a piece of paper with two pencils stuck through it. The pencils are perpendicular to the plane, therefore the pencils are parallel. Number 12. Any two line segments connecting a parallel plane have the same length if they're each perpendicular to one and hence both of the planes. Sketch an example that illustrates this statement using parallel plane P and Q. So we're calling this P and this one Q. So we're now going to do segments. So switch this to here and let's do a red one. And all they're saying is if I had a point there and a segment to there, picture a point. Sometimes 3D is tough to visualize. This is a point. So this would be like a piece of wood, and another piece of wood, and then a wooden dowel in between holding it up like so. And then I'm going to do another one, but I want it the same length. And I'll just change the color. So then I'll put this one here and make it blue. And then I will put a dot showing that it's touching the plane underneath right here and intersecting or touching the plane Q down here. And if it is 90 degrees here, and this one's 90 degrees here, and this is 90 degrees to the Q, and this is 90 degrees to Q, then, so picture poles in a room holding up the next floor level that are perpendicular to the floor and the ceiling. So this says any two line segments connecting parallel planes have the same length if they are each perpendicular to one and hence both of the planes. So what they're saying is these two, if P and Q are parallel and they're connected by two segments, and the segments are perpendicular to both, then the segments have to be the same length. So this is congruent to that. 13, the distance between a point and a plane is the length of the perpendicular segment from the point to the plane. So if I drew another segment, I'll do it dashed. No, I won't. I want it solid. Perpendicular segment, I'll use green this time, from A down to the plane, like so. Like that. The distance is defined to be 0 if the point is on the plane. So if A were down here, the distance of this segment would be 0. The distance between the two planes is the distance from a point in one plane to the other. Sketch the segment from A that can be used to measure the distance between A and the plane P. Okay, so that segment would, other endpoint would be here, and this is plane P. Okay, and it's perpendicular to that plane. Okay, page 6 brings us to the end of lesson 5, getting into three-dimensional figures here. Review the lesson summary that defines segment and line perpendicular to a plane, and go do your problem set.